Earlier in this semester, we were talking about relative frequency histograms. And this was one that represented the relative frequency for particular emissions of a sample of 65 vehicles. If we had information on the entire population, I mean, millions of vehicles, then these rectangles would get narrower and narrower and narrower, and we'd end up getting something that looked almost smooth. We get connected, and we call this a curve. The curve used to describe the distribution of this variable is called the probability density curve. It's a very dense curve. And this will tell us what proportion of the population falls within a given interval. So like between 2 and 3 or between 3 and 4. And we talk about this density as the area between two values, like from 2 to 3. And there's two ways to really think of it. We can think of it as the proportion of the population whose values are between, let's say, A and B. But you could also think of it as the probability that a randomly selected individual will have a value in that range. So have a value between A and B. So we need to think about it in both of those ways, that it's the proportion of the population, that percentage, but that also means that's the probability. So that's pretty cool. So when we're talking about this density, if we're talking about just one single value, one single point, there's no width really. And so there's no real area. So this means we're not going to be finding the probability that X equals a certain number. It's more of a range that we have to do. But the beauty of this means that compared to discrete, where we had to be really careful with less than or equal to versus just less than, it's going to mean the same thing here. Because we are going to have those, when I'm going between 2 and 3, I'm going to go from 2 all the way to 2.9999999. Where with discrete, it was 1, 2, 3, 4. With this, we're talking about, this is more with our not discrete, but continuous data. So we don't have to worry so much about being distinct about less than or equal to. It's going to be the same thing. Okay. So probability density curves come in many varieties depending on the characteristics of the population they represent. Many important statistical procedures can be carried out using only one type of probability density curve, called a normal curve. A population is represented by a normal curve is said to be normally distributed, or it has a normal distribution. Now, some of the properties of a normal curve. The population mean is going to be the location of the peak. So that highest point is going to be my mean. So I'm going to put the symbol for population mean, mu. Therefore, the normal curve is wide and flat when the population standard deviation is large. So how far away you are can make it wider if you have a large standard deviation. And if the standard deviation is smaller, it's going to be more narrow. So look at these two options. I have one that has a mean of 0 and a standard deviation of 1, and it's a pretty tall curve. But this one has a mean of 0 and a standard deviation of 2. that means things are farther from the mean, so it's more spread out. Now, when we have a normal distribution, the mean and the median are both equal to the mode. Everything is perfectly symmetrical. That's really nice to know. Now, if we look at this other option, this one has a mean of 0 and a standard deviation of 1, mean of 5 and a standard deviation of 1. So notice that the width is the same. It's just centered around a different mean. Now, another key note, since we are perfectly symmetrical, that means our normal distribution follows the empirical rule. If I go one standard deviation out each way, that's 68%. 2 standard deviations is 95%, and 3 is 99.7, almost everything. Now let's also talk about z-scores. Recall that when we talked about z-scores, that represented the number of standard deviations we are above or below the mean. Now let's take x as a value from that normal distribution, any value, with a mean of mu and a standard deviation of sigma. We can convert any x value to a z-score using this formula, and we used it earlier this year. So consider a woman whose height is 67 inches from a normal population with a mean of 64. So I'm going to find the difference between my x value and the mean divided by my standard deviation. So 3 divided by 3. This person is 1 standard deviation away. Now, if we compare these two curves, this one is in what I call the normal world, where it's centered at 0, a mean of 0, and 1 standard deviation. So 1, 2, 3, -1, -2, -3. But when we're talking about a different mean, so this is a mean of 64 with a standard deviation of 3, so 64, 67, and so forth. The 67 would line up 1 standard deviation away. And remember, we could use those z-scores to compare two values that may have different means. We're just putting them back to this normal curve. Now, a normal distribution can have any mean and any positive standard deviation. However, the normal distribution with a mean of 0 and a standard deviation of 1 is considered the standard normal distribution. This is where your z-scores live. So a z of 1 would be 1 standard deviation away. Z equals 2 is 2 standard deviations away, and 3 would be 3 standard deviations away. And then we could have -1, -2, and -3. Remember, we always count out 3 standard deviations each way. Now, to find probabilities, we are going to be using the NumWorks app, and we're going to be using the normal curve. So let me pull up my app. Okay, so on the app, we're doing inference, and we're doing probability. For discrete, we had binomial or Poisson, but we're going to the normal curve here. Now notice it starts off with the standard setup, mean of 0 and standard deviation of 1. This is what we're going to use if we're given a z-score. So what we're trying to find here is the probability that a randomly selected z-score is less than 1.26. Let's think about where that would be on that curve. Okay, so here's the curve. Here's 0, 1, 2, and 3 would be out here. 1.26 would be about here, right? And less than that would be to the left of it. So we're finding this area which represents the probability of randomly having a z-score in that range. And let's see how it looks on the NumWorks app. So I'm going to go down, and we want less than, and remember on this one, The equals to doesn't matter. So less than 1.26 gives me a probability, and look how it shows you where that line is, 0.896. So this is really nice in the fact that it's going to show me what the picture, whoops, I made this one really big and I shouldn't have, they should all look the same. Greater than 2.45. I'm going to change this to be a greater than, and notice I do not have the option for an equals to. This is always a range of values because this is continuous data. So greater than 2.45, let's see, 2.45 is going to be way over here, isn't it? Wow, it's way off to that tail end, and it's 0.007. Wow, that's really far. That's like way down here, and we're talking about this little shaded region here. Now, between negative 0.25 and positive 0.25. Well, here's my 0. Here's 1. Here's negative 1. So we're talking about 0.25 and 0.25. We're talking about this region right here. So this time we're between two values. So I'm going to go select the interval, and I can type in negative 0.25 and positive 0.25. And let's see if it shows my picture just like we drew it. Good. 0.1974. So I invite you to try the next three and draw a picture. And the picture can come straight from the app, which is nice. Okay, so bigger than negative 0.45. So here's 0. Negative 1, 1, negative 0.45 is right here. Greater than that would be this. So I'm going to pick the greater than. Negative 0.45. And that's nicely shaded. We match up 0.674. Okay, so 0, 1, 2, negative 1. My pictures are not great. Negative 1.89 would be over here. 0.73 would be here. So this one's going to be shaded kind of like that. .738. Okay, so 0, 1, 2, negative 1, negative 2. Negative 0.17 is going to be really close to 0. And 3 is way over here. 3.15 is going to be way on that tail. Let's see what this looks like. I bet that's really far on the tail. And it is. That's an area of 0.567. Now, we've been finding areas from the normal curve with given z-scores. Many problems require us to go in the reverse direction. That is, if we're given an area, we need to find the z-score that corresponds to that area. Now, suppose we want to find the value from a normal distribution that has a certain area. We'll go into that a little bit later. I really should have put that in a different spot. Let's say we want to find the value of x that corresponds to a given z-score. In other words, how far away it is from the mean, how many standard deviations it is from the mean. So if we were trying to find, we're given our z-score, and we are trying to find the x that goes with it, we're going to use this formula. So we already know how to convert to a z-score. We're going to be going backwards. Hold on just a second. I was going to give you the formula. The formula would be mean plus the z-score times the standard deviation. So you're adding however many standard deviations to the mean. Pretty easy. So we have a mean of 69 and a standard deviation of 3. Find the height whose z-score is 0.6. Z-score is 0.6. So the mean is 69. And we're adding to that 0.6 times 3. And that gives me 70.8. And so a man 70.8 inches tall has a height 0.6 standard deviations above the mean. Remember, z-scores are a way of comparing maybe things that have different means.